Today's topic is collisions, which is the application of what we saw about momentum last class. So collisions just means that two or more objects are going towards each other or going in opposite directions, or one is still and the other one is moving towards it, but they're going to have a collision. They're going to collide, hit each other, and something's going to happen. And what we want to find out here is at what speed each of the objects is going after the collision, in which direction, and what mass these objects have. So for that, we're going to use something called the law of conservation of momentum. So this law basically states that momentum is always conserved. The total momentum of a system is always conserved. Not the momentum of a specific object, but the momentum of the whole system. If we're looking at two objects colliding, the sum of the momentum of both objects will always stay constant. So let me write that down. The law of conservation of momentum, total momentum of a system, is always conserved. So this is actually only the case when there's no friction, when there's no external forces, just the two objects colliding against each other. So in every single example that we're going to solve, there's going to be no friction. So just to make sure we know that, there's never going to be any friction. If there is friction, we can't solve these problems because we don't know how friction affects them yet. So for now, all of our examples will be frictionless. Now, this is written in words as the total momentum of a system is always conserved, but it can also be written as an equation. So suppose you have two balls. One has a mass m1 and the other one has a mass m2. And one is moving to the right at a speed v1 and the other one is also moving to the right but at a speed v2. So at some point, the first ball is going to collide against the second one and something is going to happen. So I usually draw it as a collision or whatever. And then, because both were moving to the right, it's very probable that both will be moving to the right at the end too. So that's just for drawing matters, but M1 will be moving to the right, maybe with a smaller V1 final. And M2 will be moving to the right, maybe with a bigger V2 final, right? So we don't know every number, but we know some things. But to write this as an equation, we have to calculate the momentum of each, and because it's conserved, the initial momentum of both objects will be the same as the final momentum of both objects as a sum. So this is how this law would look as an equation. So we have the momentum of this one. Momentum was mass. I'm going to put that here. Momentum is mass times velocity. Don't forget that. So here we're going to have that the momentum of the first ball is m1v1. The momentum of the second ball is going to be m2v2. So if we add that, m1v1 plus m2v2, we get the total initial momentum of the system. So this is the initial momentum of the system. Now the final momentum of the system would be the mass times velocity, but with the new velocity. The mass, of course, didn't change, but the velocity did. So we're going to have m1v1f plus m2v2f. And this sum over here is the final momentum of the system. So the momentum of the first ball probably changed, and the momentum of the second ball probably changed, but according to the law of conservation of momentum, they change such that the sum of the initial momentums is going to be equal to the sums of the final momentums. So this is the equation form of the law of conservation of momentum. If you have two objects, m1v1 plus m2v2 is going to be equal to m1v1f plus m2v2f. And here is in drawing form. So in a second, I'm going to show you an example of how to use this equation to figure out the missing values in a collision. But first, I'm going to tell you two types of collisions and define them. So we can divide collisions into two types: elastic and inelastic collisions. So we have elastic collisions elastic collisions and inelastic collisions. Whether it's one or the other depends on what is conserved in the collision, during the collision. So in both collisions, momentum is conserved because it's a law, it's a general law. So I'm going to put in both, momentum is conserved. But the difference between elastic and inelastic collisions is that in elastic collisions, kinetic energy is also conserved. So here momentum is conserved, kinetic energy, Ke, kinetic energy is conserved. In inelastic collisions, kinetic energy is not conserved. So how do you know if a collision is elastic or inelastic? Well, you calculate the total kinetic energy of the system, and if you get the same value for the before the collision and for after the collision, then it was an elastic collision. If you get different values, if some energy was lost due to heat, due to work against friction or something like that, then it is an inelastic collision. However, there's also an easier way to see if it's elastic or inelastic depending on a couple of properties that it could have. So you will see that sometimes in collisions, one object hits the other and they stay together. For example, if I have an apple and I throw an arrow and it goes through the apple and it inserts itself in the apple, the two things are going to stick together, right? The arrow and the apple will go off with exactly the same speed because now they're stuck together. So if that happens, the collision is always inelastic and it's called completely inelastic collision. So an example of this one, called completely inelastic, means that they stick together. So if you get an exercise that says that the two objects stuck together, you can immediately know that it's an inelastic collision, and that means that kinetic energy is not conserved. So that happens also if you throw a piece of gum at the wall and the gum will stay stuck to the wall, or just any time that the two objects at the end have the same speed because they're together. Instead, an example of elastic collision is a little harder to find in real life because there's always sound when two things collide, there's always a bit of friction, so most collisions are neither completely inelastic nor elastic. But what can get closest to an elastic collision is a billiard balls, bolas de billar. When you're playing pool, there are collisions between the balls. And if you don't take into account the energy due to the sound, the collision is almost elastic. So when you see the way in which collisions behave that are billiard balls hitting themselves, that is basically an elastic collision. In a second, I'm also going to show you a quick experiment with marbles. Marbles would also be considered an almost elastic collision, but in real life, nothing is 100% elastic. Right? So when you're solving problems with elastic collisions, it can be mathematically a bit harder because not only do you have to use this equation, you also have to use conservation of kinetic energy. So it would also be true, you know, kinetic energy is 1/2 mv squared. Hopefully you remember that from the end of the previous unit. So we have that 1/2 mv1 squared plus 1/2 m2v2 squared is equal to 1/2 m1v1 final squared plus 1/2 m2v2 final squared. So that is what you have to take into account. If you're told that a collision is elastic, you can use both equations to generate a system of equations and that way solve for the missing variable. So now I'm going to go on to solve a couple of examples. I'm going to erase all this. And I wrote the equation again here of the law of conservation of momentum, but this time I put an I for initial in the initial speeds and an F for final in the final speeds. Something else that you need to remember is that in momentum, since momentum is a vector, we care about the directions of these speeds. So actually, these have all a direction. So these are velocities instead of speeds, And the way in which we're going to take into account the vectors is that the speed is going to be positive if it goes to the right and negative if it goes to the left. So I'm going to make sure you guys have that over here. So to the right is positive and to the left is negative. If you don't put the right direction in the problem, you're going to get it wrong. So it's really important that you take into account the direction. So our example is going to look like this. There is a 4 kilogram ball moving right at 1 meter per second. It collides against a 2 kilogram ball moving left at 3 meters per second. The 4 kilogram ball, after the collision, is moving left at 1 meter per second. So the first thing I do when I'm trying to solve these kinds of problems is draw the situation to make sure that I have all the variables. So we have a 4 kilogram ball, which is this one, 4 kilograms, and it's moving right at 1 meter per second. Right means it's positive. And it collides against a 2 kilogram ball, so it's a smaller ball, that is moving left at 3 meters per second. So left is negative. And after the collision, so we have a collision here, and after the collision, the 4 kilogram ball is now moving to the left at 1 meter per second. Meter per second. And the question is, what is the speed of the second ball after the collision? So that means what is V2F? So we're going to have this 2 kilogram ball. We don't know in which direction it's going to be moving, but we can put it to the right just so that it's positive, and we call it V2F for our equation. So what we do now is put everything into this equation. So what we got from the problem is that M1 was equal to 4 kilograms. The initial velocity was 1 meter per second positive. The mass 2 is 2 kilograms. The initial velocity of the second ball is negative 3 meters per second, negative because it's going left. And the final speed of the first one is negative 1 meter per second. So this is negative because it's going left. And the final of 2 is what we're looking for. So our equation would be, plugging here, it would be 4 times 1 plus 2 times negative 3 equals 4, the same mass, times, now it's negative 1, plus 2 times V2F. So it's a pretty long equation, but notice that these are all just numbers. So let me solve. Here it's 4 times 1 is 4, 2 times negative 3 is negative 6, so 4 minus 6 equals negative 4 plus 2V2F. So 4 minus 6 is negative 2. Pass this one to add, plus 4, it's going to give us 2 equals 2V2F. That means that V2F, 2 over 2 is 1 meter per second. Right? And it's positive, so that means that we were right at guessing that it was to the right. If it had given a negative number, it would have been to the left. So the answer is, the second mass is going to be moving at 1 meter per second to the right after the collision. Probably, if we tested if this is an elastic or inelastic collision, it's going to give inelastic, because it has to be some very specific numbers that I didn't really think about to give an elastic collision. But we could find that out by putting it into our equation. So we could calculate 1/2 times 4 times 1 squared plus 1/2 times 2 times 3 squared, and check, so we don't know if that's equal to 1/2 times 4 times -1 squared plus 1/2 times 2 times 1 squared. If this gives equal on both sides, it's an elastic collision. If it doesn't, it's an inelastic collision. And it probably will be inelastic. I'm not going to do this, but you can check if you want to.